It's a great pleasure to introduce Kavita Ramanan. Kavita is a professor at Brown University, and she's also an associate director at the Institute for Computational and Experimental Research in Mathematics. She's a very well-known applied probabilist. We have intersected for many years. She works on large deviations, Markov random fields, interacting particle systems. I used to work in large deviations, but then I diverged, and Kavita has stayed close to those subjects. So today she was going to talk about some work on SIR dynamics and interacting particle systems. She, as I mentioned, is very well known. Her research has been recognized by a number of very important awards, including the Vannevar Bush Faculty Fellowship, a Guggenheim Fellowship, the Newton Award, and the Erlang Prize for, from the Applied Probability Society of Informs. She's an elected member of the American Academy of Arts and Sciences, fellow of a number of societies. I'm not going to go through the entire list of achievements because I would like to listen to her talk. So with that, Kavita, it's a pleasure to have you here, and we're looking forward to your presentation.
Thank you very much for that overly generous introduction, and it's a great pleasure to be here in this beautiful building and to have a chance to share just some of my thoughts with you and to see, maybe get ideas on ways of collaborating and going forward. So I'm going to be talking about a unfortunately topical subject, which is related to sort of epidemiological models and spread of diseases. And so please interrupt me at any time. I'd love this to be informal and ask questions as we go along the way. So let me start with the context and motivation. So as we know in examples in epidemiology, you have the spread of human diseases, and the way they spread is through your human social contact networks. So which could, typically not be planar networks, right? Because your social contact networks could be how you fly and whom you meet, and so they're not necessarily just purely planar. And how are they determined? They can be determined using sort of location tracking technology, contact tracing, et cetera. Or, much earlier, people are still interested in studying animal diseases, this is sort of a chart which I saw from some applied paper, which was studying chronic wasting disease in cattle farms in Pennsylvania. And so this is just a plot of how people transported cattle from one place to another, and they were trying to document that to try to see how this chronic waste disease spread. And this is over a 7-8 year period. And so it was much slower spread of epidemics. Again, this is some data collected from shipment of farm animals, and this is, of course, very much a planar network because we're a geography here. Or you could think of spread of computer viruses, which again is then going through the internet or some sub-network on that, which is again not a planar network. And again, you can determine sort of these maps of internet from various data sources. This is one of the earlier ones from Bell Labs, the OPTI projects. And then you also have the spread of epileptic seizures in the brain, which then are going over neuronal networks, so which are again a different kind of network. So some key observations in the applications above is that the underlying network graph can have different geometries depending on the application. And these geometries can often be random because sometimes you can have some links that are not connected or there's some probability that they'll be connected, they're not. Or it could also be that everything is deterministic, but the network itself is growing all the time like the internet. And so if you want to sort of understand what's happening in any one network without actually finding out what every link is, a good way to, robust way to do that is to think of it as coming from some random ensemble, which has similar properties in terms of its connectivity, et cetera. And then that makes it more tractable to say something that is not too specific to one network, but to some ensemble of networks with certain properties. So often you model this underlying network in terms of a graph or a random graph. And real node networks are often sparse in the sense that the number of neighbors that any one node has in that is sort of bounded with relative to the size of the network. So, if the population of Boston is increasing all the time, it's not that your network of friends is increasing proportionally, right? So you might get a few more, but it's not really going to go. So it's going to remain bounded even if you get a very dense network. So that's really a lot of measurements of real-world networks have shown this to be the case. And the dynamics that you have on this, so with the virus spreading or anything, can also take different forms and different applications. For today, I'm going to consider the case when each of these nodes can be in some finite state space, and so you just have this in continuous time, it's evolving. So I will be more precise about that shortly. Okay, so these phenomena are generally modeled by something called, so there's stochastic high-dimensional dynamics on a network, and these are modeled by looking at this underlying network graph, which is a collection of vertices or nodes representing these either individuals, computers, farms, whatever it may be, and then their connections, okay, and which itself is possibly random. And of course, in a more refined, complex model, you might also consider that these networks themselves are evolving. For the purposes of this talk, I'm going to have the networks be static for the moment. They could be random, but they're not evolving in time. Okay, and then the instantaneous stochastic evolution of any of these particles typically depends on its own state and also that of its neighbors or possibly its histories. Okay, and so these are called locally interacting stochastic processes, and I will just use this sort of twiddle to say that two particles are neighbors over here, and dV, or is the degree of the particle, is the number of neighbors, so that's 3 over here and 1 over here, for example. And V bar will denote a vertex and its neighbors. Okay, so what is the goal? The goal is to develop principled approximations for these very complex networks when the size of the network is very large. Okay, so let's actually get to some idealized math models of epidemic spread. So this is sort of general broad context and motivation. So let's fix some underlying interaction graphs, your favorite graph that is relevant for the application. And then the state of each particle lies in any one of 3 states. It could be susceptible, so you're susceptible to a disease, but you're healthy at the moment, or you could be infected, or you could have recovered, and let's consider for the moment, you're looking at a disease in which if you've recovered, then you're immune, so you can't get it again. Okay, we can look at various different types of models. We wish COVID were like that you could only get it once, but okay. Then that the transition rate, thank you, of a particle is, how it evolves from S to I to R, or all of these things, are governed, of course, by the neighborhood structure of the states of all your particles in your neighborhood, as well as your own state, and as well as 2 other sort of parameters here, which is the infection rate and the recovery rate. So you're given some possibly time-varying functions. Your beta is the infection rate, rho is the recovery rate. And then your transition from S to I is simply going to be proportional to the number of your neighbors who are infected. Okay, so that's what sort of this is saying, where if your Z was going to be 1 if you're infected. Okay, so you just count the number of your neighbors that are infected, and then you multiply that by the infectivity rate. That's the rate at which each particle is transitioning from S to I. Clear? And the rate at which you transition from I to R is really independent of how many contacts you have. That just depends on how long it takes you to recover. Okay, so the I to R transition rate is just some fixed recovery rate that we say rho T. Okay, and so of course you only can go from S to I to R in this simple model. Okay, and now of course there are various variants of these models, which I'll just mention 2. So you could, in some cases, people who are trying to study epidemics, there's this little intermediate phase where you become exposed, and so you're sort of going to be infected, but you're not yet contagious. And then you go to and you could do it the other way around, that you immediately become infected, and then there's some time when you're still infected, but not contagious. But in this case, okay, E is you're exposed, but you're not yet infecting others, and then you go to I, and you get to R, and then you have similar rates Okay, from S to E is the same as before. It depends on how many people around you are sort of infected. But your rate from I to R is still just some fixed recovery. But then you also have this intermediate transition going from exposed to infected, which is again independent of how many people you're exposed to, because you're already infected and it's just about some amount of time after which you're going to become infected. Okay, so you have these different models. Then you can have the model where you have only two states. You're either healthy or infected, and then once you are infected, you recovered, you could again get infected. Okay, and that's called the SIS model. So there are many such models that you could have. And now there are no transitions to recovered because there's nothing like full immunity. There could be more complex models in which you say that each time, the next time you're going to get infected, maybe you have a faster recovery time, et cetera. So there are many, many things that you could put on these models. But let's consider the most simple SIR model that we considered. These are all examples of what are called locally interacting Markov chains, which means that the transition that any one particle is going from one state to another doesn't depend on the entire configuration, but it only depends on its local neighborhood, right? The states of the particles in its local neighborhood and itself. And it doesn't depend on the history for now. We can do things with history, but I'm keeping it simple for now. And like I said, we could also consider non-Markovian models, which makes sense because even your recovery period need not be what is an exponential distribution. It could be that, you will definitely not recover for the first 2 days, the disease. No one ever recovers that fast. It'll only take much longer. So there are things where you have to put sort of non-Markovian versions of the models, but don't worry about that. Okay, there's just some rate. So what are the quantities of interest that one would be interested in such a model? You would be interested in the fraction of the population that's infected, the fraction of the population that is recovered, things like that, or how many people there are clumps where everybody is infected. So you might be interested in things like neighborhoods, or is there some sort of place where there is one person who's infected but all their neighbors are not, So questions like that, right? So things that you want to know, and you could also ask things about the history of the process. Okay, so this is captured for it doesn't matter, you just think of all these fractions, but it's rather than talk about various particular fractions, it's just easy to say that that's all encapsulated in a mathematical quantity called the empirical measure. So whenever I say empirical measure, think fractions of various particles in various states or fractions of configurations in various states. That's captured by what's called the empirical measure, okay? But these are just average quantities in the system, which are macroscopic quantities you're interested in. Okay, so that's a very natural thing you would want to know, right? Like how many hospital beds do you need? How many fractions of people were infected? On the other hand, you might also not just macroscopic quantities, you might want to, you only care about how you're evolving in this whole epidemic. So you might care about a typical particle and its evolution. And what's the probability that I, as a particular person in this system, will get the infection? Okay, so these are sort of two things that you might be interested in, macroscopic quantities, typical particle dynamics. Okay, is that clear? Okay, and it'll obviously depend on the underlying graph. That's why I always have this G sort of hanging around there. Okay, and I'll use O to often denote a sort of typical particle. By typical particle, you can think I choose somebody uniformly at random from the population, and that's my typical person. Okay? Okay. So, like I said, these are very rarely, almost not, amenable to exact analysis, right? So what one tries to do is one wants to try to see if one can get principled approximations for these, which are asymptotically, rigorously shown to be exact as the system size goes large, okay? And so these will give you some sort of reduced order modeling. So you have this sort of large N, you're suffering from the curse of dimensionality in order to understand these systems. Can we do anything to simplify this analysis? Okay, so is there some sort of limit that we can describe more nicely as the system size goes large? And then can one autonomously characterize my evolution or one typical particle evolution in this large system? Okay? Any questions? Yes?
I'm struggling a bit to understand what a random graph is. Can I by your definition, can you get any information on the clique structure or the spectrum of the graph or anything?
Yeah. So a random graph, just keep this as a particular example, that if you want, you can take a graph in which you connect any two vertices independently with some probability, right? You could say that my connection probability with anybody is some random probability. So you'll have different ensembles, and then depending on what random graph you decide, what ensemble you choose, there's lots of analysis that people have done in the random graph literature to understand what is the typical clique structure, what is the typical. And that's exactly a very good question, because if you actually see a real network and you have some idea of what would be reasonable for its clique structure, et cetera, you would choose a random graph ensemble that has those properties. And that would be a good modeling tool. Yes, thank you. Okay, so what is known already, right? So what has been really well studied is the case when everybody is connected with everybody all the time. Okay, and that's the complete graph. The complete graph just is a graph which has edges between every two vertices. Okay, so that means I can get infected by anybody, in the whole population. So a well understood setting is, this is the case, right? And now I think sort of one thing that you should understand is that if we're all evolving independently of each other, sort of the extreme case where we're actually not interacting at all, and we all have our just each evolutions, and I take the average of all of us, then this is a really well understood quantity in probability, right? By the law of large numbers, when you have a lot of independent things adding up, then you know that they behave like their mean, okay? But now we're actually interested in interactions, and can we still say something about the sums when they're interacting? And so the point about when you have complete interactions, and my interaction is always of order 1, and it is always going to be, since it's symmetric, that's another assumption, that it's symmetric with respect to all the people in the room, in which case then any one person is only going to affect me 1 over my degree, which is going to be 1 over n, if n is the population. And so that's going to decay when the system size gets large. So asymptotically, the influence of any one person on any other one person is going to go to 0. So sort of asymptotically, they're becoming independent, so you might expect that you have similar features as you do when everybody's independent that you aggregate, okay? In the sense that you might expect that there is some sort of deterministic dynamics coming out of that. And that is really true, that you can show this under, of course, various circumstances, that even when you're interacting and you're on the complete graph in this way, things are all exchangeable, then the limit will be deterministic. It's sort of a generalized strong law of large numbers, and this global empirical measure or averages will concentrate around its mean, and we can also, in fact, describe the dynamics. So this is just a little bit to just say that in words. So not only will this empirical measure, so averages, converge, what does it converge to? So it will converge to the law of atypical particle. So what do I mean by that? Just think about it this. If I have a large system and I want to know what is the probability of there being like 10 people, or like a fraction of half the people being infected, it's going to be the same as the probability of any one particle in an infinite system being infected. Okay, that's what this is saying. Okay, so it turns out that that can be shown quite generally for these kinds of complete graph systems, and you can actually then write down an ordinary differential equation that the details of which you don't have to necessarily follow, but it's just an ordinary differential equation, but it's nonlinear on the right-hand side, which explains how this empirical measure or the law of the typical particle, which are both the same in the limit, evolve. Is that clear? So that's quite remarkable if you think of it. Of course, many people may know about this already. They're called mean field limits or mean field dynamics. But that's pretty remarkable that you have a really, really large system, and you want to understand how the whole empirical measure is. If you're going to simulate, you're going to have to simulate all these n particles, run it, then take averages. But in fact, in the limit n, it looks deterministic, and it just is a one-dimensional ODE, right? So that's remarkable reduction. And so that's why mean field limits are so powerful, and they're used ubiquitously in all sorts of applications in engineering, in science, epidemiology, not only for the SIR model, but for many, many such locally interacting particle systems, right? Okay, so like I said, what are the key aspects that allow this to happen? The particles are asymptotically independent because of this, the degree going to infinity and your influence being 1 over the degree. There's a symmetry, which is what these particles are exchangeable. That is, I interact symmetrically with all my neighbors. And once I know how the global empirical measure behaves, I also know how any typical particle behaves, because every typical's evolution only depends on everybody else through the averages, right? Because remember, in your SIR model, the way you go from S to I depends only on the fraction of your neighbors who are infected. So that's only a quantity that depends on this global empirical measure. And so once you get this global empirical measure from generalized strong law, you also get the evolution of the typical particle. So that's amazing. Okay, but in the case of the SIR model, these nonlinear ODEs, just based on sort of heuristics of sort of dynamics and understanding that, okay, what's the best deterministic approximation to these large systems, it was posed by Kermack and McKendrick without actually, sort of any concrete proofs. It was posed in 1927, and then it went into hibernation for a while. And then it was revived by Anderson in May 1979 in an influential paper in the Royal Statistical Society, I believe. And so then, people started using it a lot to make predictions of SIR. And, if you've seen in the newspaper, if you've seen anything called the R0 number for the epidemic and things like that, that's really coming from these models, okay? So it really was used a lot in practice. But various modifications of these dynamics have been used. However, as I mentioned, real-world networks do not look like a complete graph, okay? So while these models were sort of used as ad hocs, they produce some information, better than nothing, they do not really capture real-world networks and how they spread, okay? Okay, so one question is, okay, but it might be that the mean field approximations, even though mathematicians haven't bothered to rigorously prove that they're good in these sparse case settings, maybe they're fine. And it's actually true that a huge literature in neuroscience and different science and papers just say, okay, by an ad hoc mean field approximation. And it, because for lack of a better alternative, they use that. And it's better than doing nothing, okay? But now let's look whether they actually work well on any graph. And if you just take a ring where each person interacts with only 2 neighbors, and then you plot here the probability of being infected versus time, and you will see here that green is the mean field approximation. This is what it predicts, whereas the simulation of this ring for some large n is actually giving you a very different curve. Okay, so this is saying that really mean field approximations do not work well on all graphs. Okay, may not work well in many graphs. So this motivates why you want to understand how these dynamics behave on sparse graphs, okay? And what are some of the challenges? So now, just keep the ring in your mind, though we will, of course, look at more general, graph structures. Now, if you keep the ring in your mind, and if you think about all the key ideas that allowed us to get this nice deterministic approximation in the mean field setting, let's see what are the challenges. So again, we're going to go away from the complete graph or even dense graphs and go to sparse graphs. And you can either think of the Erdős-Rényi graph that I mentioned earlier, which is any 2 people are connected, with some probability that would be inversely proportional to the population to keep the average degree bounded. So sparse graph, or you can just think of the circle. And what is the contrast with the complete graph setting? Neighboring particles will not be asymptotically independent. If I only depend on my 2 neighbors, even if the population of the whole the cycle gets really large, I'm really going to still be really strongly influenced by what my left and right neighbor does, right? So you're not going to have this sort of I'm sort of becoming independent and things are going to be. We cannot use that argument or to expect sort of something nice to happen. Moreover, even if by some miracle I manage to find what averages look like in the system as the system gets large, I still cannot find out what the typical dynamics is of any person, because my dynamics doesn't depend on the global average, but it depends just on how many of my local neighborhood is infected or not, right? probability of me evolving is going to depend on my local neighborhood, on how many of my local friends, not who in the whole of Boston, the fraction of people in Boston who are going to be infected, right? So, so therefore, that's another thing. I don't get immediately my typical marginal dynamics from my knowing the global empirical measure. So also, you cannot just expect to take a limit and say, oh, I send the population size to infinity. I need to know what is this graph structure. The topology and the structure of our connections is going to be important, even if it's sparse, right? So whether I have my like if I have 3 neighbors or 4 neighbors, is it in a tree structure or is it on the lattice? It's going to be very different. Okay, the way your influence is spread, it's going to be very different. Okay, so one notion is then, how can I even get any asymptotic limits if I can't just take n to infinity? It means that then I have to embed whatever problem I'm looking in into a sequence of problems, right, which I send to infinity, where the graph structure is somehow maintaining the same type of topology locally, right, because that's what's going to influence my dynamics. So luckily, there's some really nice work by Benjamini and Schramm, which is now more than 20 years old, which tells you what is this notion of graphs converging to some limit graph in a way that maintains the local topology. Okay, so of course, all this is saying that if I consider a sequence of graphs, they converge to a limit graph. If for every finite neighborhood, I look at a finite neighborhood of my graph, there should be a large enough n such that they're isomorphic. That means they look more or less similar. There's a mapping of the vertices to those other vertices such that the edges all coincide. Don't worry if you don't follow this definition, let's just do it by pictures. Okay, so if you have a cycle, then locally it simply looks flat, right? And so if you believe in local convergence, you can join the Flat Earth Society and claim that we have a flat Earth, right? So it's really saying that locally it looks flat because I only want for every finite distance, when n is large enough, this is going to look like a line. Okay, so that's one thing. The cycle graph will be converged to the line. And it turns out that if you take this other graph, which is you take all graphs on n vertices, which have exactly, every vertex has exactly k neighbors, okay? Or in this case, d neighbors, right? And I choose one at random. There are only finitely many, so I can choose all of them with equal probability. That's called a d-random regular graph. Is that clear? What it's particular graph. So if whatever graph you're looking at, you feel that everybody has exactly d neighbors, this d-regular random graph is a good model for it, right? Okay. And so you take that and you take a root, which is sort of telling me what your typical particle is, which is just chosen uniformly from that on that graph, right? And if I look at it, that converges to what is the d-regular tree here. This converges to here, where the root is a center. What is a tree? Well, we all know you have 3 branches, and then each of them has another 2, and this 3, etc. You just keep branching, right? There are no cycles in this graph. Everybody has exactly 3 vertices, 3 neighbors, okay, as I know. Okay, so that's a little bit of a surprise because it's not so obvious as the cycle to the tree because you know the random regular graph, for example, we know a 2 regular graph, a triangle is a 2 regular graph, right? Because every vertex has exactly 2 neighbors. So that has cycles, but we're saying as you get larger, if I keep choosing 2 or 3 regular graphs, then in the limit, I will not have cycles. But it's not saying I don't have cycles, but it's saying that if I look locally, the probability of seeing a cycle that is small is going to go to 0, okay? The graphs will still have cycles, but the probability of seeing it goes to 0. That's what this is saying. Okay, and then you can have this Erdős-Rényi graph that I told you where everybody is connected uniformly at random. So beautiful thing, it says that this graph converges to what's called the Galton-Watson tree, which has been introduced by Galton and Watson to study genealogies. And now it's used a lot in genetic models as well. So what is it? You start with a root, then you choose a random number of offspring. So it's a very, natural model for population genetics. You have a random number of offspring. Each of them independently at random have another, random number of offspring, etc. Clear? With the same distribution, the same number. So that's called the Galton-Watson tree with some distribution. So in the case of some offspring distribution, in the case of the Erdős, that offspring distribution is what is called a Poisson distribution with some parameter p, which is exactly the same parameter that you used in your probability of connections. Okay? The details of which don't matter, but there's an explicit distribution of the offspring distribution that this converges to. So it's clear? So there are all these convergences. There are many, many other examples of random graph ensembles converging to random trees. Okay? Okay. So like I said, our focus is looking at sparse graph sequences. And so the framework, at least we know what is the question we want to ask now, because we know a way to embed graph sequences and such that the graph converges to a limit graph. Then you might ask, okay, then can I understand how the dynamics looks on these large sequences of graphs, and I send the n to infinity along the sequence, do I get some nice description of the dynamics? Is that clear, the question? Any questions? Okay. Okay, so let's look at what results, and this is joint work with Juniper Cocomello, who's a student of mine from Brown, and Ankan, who is a postdoc right here, who's a former student, so yeah. So if you have any hard questions, please direct them at him. Okay. So let's look at the results for the continuous time SEIR model. So with possibly time-dependent rates. So like I said, what we're interested in is what is the fraction of people in susceptible, infected, recovered, et cetera. So, and you could choose any of these sort of random graph sequences. Don't worry if you don't know what the configuration model is. This is just to quickly tell you, you choose some sequence of natural sequences which people use to model real-world networks. The configuration model, for example, is very much used. And each of them comes with an associated distribution, which is related to this offspring distribution in the Galton-Watson tree that I said. So for the Erdős graph, you have the Poisson distribution. For the configuration model, you can choose any offspring distribution that you want that's related to your configuration model. The uniform random regular graph, your offspring distribution is just always a fixed number. Right? So you have exactly 3 offspring. Okay. So, and you can look at many others, which I'm not going to talk. Preferential attachment, maybe some people have heard of that. So there are different graph models which will give you some limiting random trees. And for the results, I'm going to use, if you have this distribution, I'm going to use a certain function that depends on that. You don't have to worry too much about what this function is, but it is in fact what's called the moment generating function associated with that distribution. Okay? Okay, so we have a graph, we have some dynamics. What have we done? We embedded into some sequence of random graphs that has that graph's properties. And we take the limit and we have this new distribution and we get this function mu. And so this work with Juniper says that these fractions that we were interested in, fractions of susceptible, exposed, infected, et cetera, converge to a limit. And this limit is given explicitly in quite simple form. So it is a deterministic limit again, even though the same principles don't hold. It turns out there's still a deterministic limit. And so this is, just some explicit function in terms of these quantities fi and small fi. So I have to tell you what they are. And they are satisfying a bunch of ODEs. Okay? The exact form of which is not important, but it's just like a system of 3 ODEs. Okay. And this new bar, you don't have to worry, it's a certain distribution related to nu that comes up in the calculations. Okay, and then there's some initial conditions. Okay, so these are just to show you that they're very simple ODEs. However, they're nonlinear over here, so they're not, if you know ODE, it's not nice and Lipschitz on the right-hand side to show there's a solution, unique solution, but one can show that there's a unique solution. Okay. So this is a really nice system of ODEs, and now we can run these ODEs to understand what is the fraction of susceptible, infected, et cetera, that you might expect in the system. So is it clear what this is doing, what the statement of the theorem is? Yes? Okay. So now you can say, okay, well, okay, this is some math theorem. You send n to infinity, you're doing something, but how do I know whether n has to be some astronomical number before it even, is going to be valid? So you can run your dynamics on an ER graph, for example, the Erdős graph, just of 500 nodes, which is not a lot for the kinds of applications that we have. And you can see that the simulations are dot on the, so these are just two different simulations, and both of them are just going right on the ODE, right? So you can't even see that there's a difference between them because they're all going one on top of the other. These are different lambdas, which are different types of graphs, really. Okay? So it seems that at least for n equals 500 or even n equals 300, this seems to be a reasonable approximation. Of course, if you're a mathematician, you would want proofs of error bounds, which we don't yet have. We have it for very simple cycle diffusions, but okay. And then this was just assuming some constant infectivity and recovery rates, okay? But in many cases, in actual epidemic modeling, they do want actually time-varying rates. For example, you have seasonal. Let's say, oh, winter's coming, you're going to have more, or various reasons why you're going to, or maybe like you've got a more virulent strain now, so you're going to have more infectivity, et cetera. So you have these you want time-varying models. And it turns out that the usual math techniques that are used for constant models, even in the SIR, don't really hold in this time variable setting. And so in the constant model, there's only one parameter really. You don't care about rho, which is the recovery rate, and beta, the infectivity. You only care about their ratio, okay, which is quite easy to see if you know a little bit of probability. But when they're time varying, the ratio is not enough. Unless the ratio is completely constant, which in the case that they're same. But here's an example where the ratio is varying according to this. And they have two different scenarios where rho is increasing, one rho is decreasing, and beta is simply chosen such that this still holds. Okay, so their ratio is following some time varying thing, but you'll have completely different evolutions of the epidemic. Okay? So, just to try to tell you what information can you extract from these ODE models, you at least get some insight into what parameters matter for your model. What should you measure? What should you if it's time varying, you can't just be looking at ratios. You have to actually look at each of these separately. You have to be able to measure. And how they evolve changes completely how the dynamics of the epidemic evolves, progresses. Okay, and then you have similar ODE characterization. I didn't write it down for you, but it's just one more 4 systems, coupled system of 4 equations. And again, now I've just done the ODE and the simulations for n equals 200, not 500, and you'll still see good match with a little less of an absolute match than the 500 because you haven't yet reached that asymptotic. But even for 200, they're very reasonable, okay? Okay, so you can see that there's some error bounds in for some of them because 200 is pretty low. Yes?
What do you think? It's
those things are the confidence intervals. They're not.
No, I'm just asking a more basic question.
Oh, yeah.
The y-axis is like the percentage of the population that's infected?
Yes. So actually, SEIR, so these are these different colors, so S, E, and I. If you know S, E, and I, you know R. So the S is the susceptible, E is the fraction of exposed, and I is the fraction of, so the green is the 3, that's what is being plotted. So that you know exactly what's happening in the epidemic. Thanks for the question. So that's why there are 3 things everywhere. Okay. Okay, those are the 3 fractions we want to track. Okay, so just to say a little bit about comparison with prior work, there was just one work that looked earlier in the Sparse regime, or 1 or 2 works, which looked at a particular class of graphs with constant non-time varying rates, and they got some an ODE description. But our proof, an SIR model on its own with constant rates can also be related to something in math called a percolation model, and people have used that to get some insight. But ours doesn't go through all those mechanisms in order to actually prove, but we in fact have It holds for a more general class of graphs, allows for time-dependent rates, which are really important, and it extends to SEIR type models for which the other results do not exist, and for time varying, et cetera. And in fact, some of our work also extends to non-Markovian models, not that you have an ODE description, but now you have a more complicated description, but the basic ideas evolve, continue to hold. Okay, so once I talked about the evolution, but really one thing that people are very much interested in these epidemic models is what's the outbreak size? And the outbreak size is defined as something that you look at the end of the outbreak when finally it's over, and you say, what is the fraction of the population that was infected at any time? Right? In the SIR model, that's just what is the population, the fraction of the population that was infected and recovered, right? And that's something that you really want to understand. And so it turns out that we can, in fact, solve quite analytically in this case, because it's a simple SIR model. But in the sparse graph setting, you can see how it depends on the topology of the network. You can see through this equation how the outbreak, so remember this nu over here, that was capturing the topology of the network, because it's telling you what the offspring distribution is, which is telling you what your neighborhood looks like, which is essentially capturing what is your topology of your network, okay? So it's the connectivity structure of your network. So it's a way to really, this fixed point equation tells you how the outbreak size is connected to topology, whereas in mean field, you just don't pay attention to topology at all. So it's even when you have dense and not a complete graph, it's just saying, I don't care about the connectivity structure, I just send everything to infinity and I get a result. But we know in real world applications that actually the topology matters, and so this is a way of capturing that dependence. And so this here is actually plotting, here this is a kappa regular tree with different kappas, and this is telling me what is my fraction of people who were ultimately infected, okay? And so these plots are for n equals 50, and it's sort of converging, and this black one is like what our limit says. So this also tells you the rate of convergence in some sense, so you can see that when you're in 2 to 400, you're more or less there. So even in the limit at infinity, you can see that when you're sort of n equals 500, you can use this to approximate the outbreak size of your epidemic. Okay, so it's just a simple analytical fixed point equation. Imagine if you use simulations, you would have to run this really large N500 system in order to actually, and then run it many times to see what's the probability of the outbreak. Okay, and then in the time homogeneous setting, the outbreak size is the same whether it's SIR or SEIR. The dynamics is different, but the outbreak size will be the same. But this is not true for time varying models. And so for SEIR models, you can also get a more involved fixed point equation that you can solve to understand what is the effect. The outbreak can actually change in a time varying setting if this SEIR. Okay. And now you can say that, well, okay, but maybe I could have just used mean field approximations all along. Why bother with these other ones? Even though the complexity of this is just as good, and this is asymptotically rigorous, so you might as well. Good to get some insight into what commonly used methods, whether they're good or whether they don't. And you can see the mean field always overestimates the outbreak size. So, if you're comfortable with mean field, you can say, well, okay, at least I'm overestimating. In this case, we can actually prove this. And here is the plot of actually what's the simulations, what we say. This is for n equals 400, so there's obviously some deviations here. But this is for, and also the infectivity rate is low. So there's also some rate of convergence also depends on that. But the blue is the mean field. So it always is overestimating things. And here, again, for n equals 400 with a slightly higher infectivity rate, even at n equals 400, the red and blue. So for small values of kappa, it's bad. But for large enough values, at some point, it's good. So you might actually want to develop these. So we can actually prove these things. And this is yet a higher infectivity rate. So it's also useful to say that the mean field approximations actually work quite well in very large kappa, which sort of also is making sense. That if I really have a large degree, it's starting to look like a more dense network. It's not completely obvious mathematically that this will be true, but this is giving you some idea of what's the rate of convergence, how can it depend on beta, which is an analysis you can do if you want to, because we have these ODEs, but we haven't done the full analysis. Okay, and there are relatively few such understandings of, rigorously saying when the mean field approximation will hold true or not. So that's sort of useful. And yes, please.
I have a question about
yes, please.
axes again.
Yes.
When you talk about an outbreak, is the vertical axis going to 100%?
Yes, so because here the infectivity rate is very high.
Okay.
So ultimately it's going, all of them are getting infected because this is on a finite graph.
Okay.
So on a finite graph, then in a deregular tree, then this is very close to one that almost everybody will get infected.
Is that the case with all of those graphs?
Yeah, here, yeah. So not here. We haven't gone all the way. So up to kappa equals 16, it's not yet, right? So here it's not true, right? So when you just have kappa equals 2, there could be, so just think about kappa equals 2 is just a cycle, right? And if somebody is recovered on my left and somebody is recovered on my right, then I can also recover. So there's, I may not ever, get infected,
okay.
Right? If I'm susceptible and somebody on my left and right get infected and also get recovered before I get infected, I will remain healthy,
Okay.
right? So for small, you don't always have to reach 1, but as the chances of you remaining uninfected become smaller as kappa goes large.
Okay, so
that's always true. Whether you reach 1 and when you reach 1, you can do the analysis from the fixed point equation.
okay, but the horizontal axis then is not time.
No, this, I said here the horizontal is the degree. So I was showing these, this is for the degree, because in the outbreak size there's no time.
Okay.
It's just a fraction, which is at time equals infinity. So there's no evolution in this when I'm talking about, but thank you very much. Make that clear. So here the vertical axis is just a fraction between 0, 1, like 0.5, 0.7, 0.9, which is telling me what is the fraction of vertices who ultimately got infected. And here is the different types of graphs, depending on what is my neighborhood structure, right? And so I just plot these points individually. I'm just connecting them to see the trend, but they're just separate points. Clear? Okay, great, thank you. And yes, so here you don't always have to have a full outbreak size that's 1 for sure. Otherwise, it wouldn't be an interesting quantity to study, right? But as your degree gets larger and larger, then you get closer and closer to an outbreak size that's 1. Okay, but it also depends on your infectivity rate. If your infectivity rate is low, it'll take much longer to get there, right? So it's a combination of all these factors that will determine when you actually reach your outbreak size. So maybe I'll skip the comments on the proof. I'm very happy to talk to people who want more information on the math. But you can generalize this not just to SEIR, but what are called compartmental models, which are used, a certain class of compartmental models which are used, where you could even split from here to maybe 2 types of infectivity, maybe 2 different distinct virus strains. And then you could maybe even go between the 2, and then you could go to an absorbed state, things like that you could study. But we don't, in this, allow ourselves to come to the SIS model, for example, to come back. Then these approximations are not exact. They're only approximate, even in the limit. Okay? Okay, so these forward compartmental models, which a lot of people use in actual epidemiological modeling in simulations, can also be reduced to ODEs. So just to summarize, what we've done is you have these very complex, high-dimensional interacting particle systems that are describing some epidemic spread. And so for a subclass of them, of the form that I told you, these compartmental models, SIR, SEIR, and so on, we've been able to obtain asymptotically exact reduced order descriptions in terms of a much reduced number of ODEs. And admittedly, it's only for certain graph structures, so there's a lot of interesting questions that still remain. So it could really be used possibly in conjunction with simulations and integrated into the hybrid analytical simulations to give you much more insight. So for example, if you want to say, okay, what is the parameters, how should I change the graph structure? For example, what sort of social contact laws should I sort of enforce by changing the graph structure in order to bring things down for something like this? So I'm not saying that this is exactly reflecting the world, right, because the actual network may be more complicated, but it can give you some ideas on what would happen, like what is more important. Should I work more on reducing the beta or increasing the rho or doing various different things, or should I change the graph structure? So it gives you a way of sort of analytically getting insight into things, and then you can use your higher order full simulations in those parameter regimes in order to get more refined insight into a particular application. And of course, these ODEs can in principle be analyzed to get more qualitative insight than the ones that I said, and to study optimal control and mitigation policies, such as those that I mentioned. And there are many other future directions. For example, relating these reduced order descriptions to real-world network data. If you actually use those real-world network and you use one random, which random graph should you use from the ensemble? And then does it really provide a good approximation or not? Or should you be using more lattice models and these are not so valid? And then you have, like I said, more other types of epidemic models where you don't have immunity, the more ones like COVID where you would come back to be infected. How do these reduced order descriptions describe? There we know that we can have ODEs which are sort of, not ODEs, but which are non-Markovian processes. We've proved that in work with Ongun. But do these reduced Markovian descriptions give you accurate enough information? When do they do so? That's a very interesting open question from a mathematical and practical point of view. Thank you very much.
Thank you, Kavita. Excellent talk. Let me start with one question, and then the graph structure can be completely arbitrary, random graph structure? No.
No.
You had randoms.
So certain classes which lead, where you can show that this GN converges to locally to a limit graph. And typically for what we have done so far is for unimodular Galton-Watson, which is all of these models. But for example, the preferential attachment goes to a random tree, which is slightly different. I think that can be analyzed, but we haven't done that. Yeah.
What if you have random graph structures where maybe there is a high probability of connecting within a certain click, but then a small probability of connecting across clicks?
Yeah,
which
that's
may be more typical of
with many of real world.
And then, obviously there's a lot of connectivity within a town, but
Yes.
then you move to another town, less connectivity. These two-level type of graphs.
Yes, so what we've looked at, one is what we called hybrid graphs with Juniper, which I didn't present, where you might consider sparse networks of dense graphs, which is sort of what you're saying. I'm thinking of this graph as being, some local where it's very dense, and therefore with many cliques, and then across that it's sparse. And some of this can be extended if we make, of course, some assumptions on how dense, and the dense is very dense, like a clique almost, and then, yeah. But if it is, so we can do that as well, and we can get models. But, and of course, those ODEs are different. But if it is just a very arbitrary graph, we don't know, and that was sort of one of my questions, saying that we should look at real-world network data and then understand better what graphs of these types would be reasonable approximations, and then do they actually capture that? Thanks for the very interesting question.
Thank you. Any questions? Yes.
Yeah, two questions. One is, I'm trying to...
Just, yeah.
Oh, sorry.
Thank you.
Two questions. I'm trying to put the context, find the context of the Galton-Watson work. Is it like from the 1890s? Who are these guys?
Yeah, so it is from that century, but I don't remember. I think maybe if it's in the 20th century, but I don't remember
around
exactly
the turn of the
when.
last century.
Yeah, but when they're actually studying, early last century.
Okay, I know who the guys are then.
Yeah,
From
Britain.
Yeah. The second question is, if you had a family of graphs where you could explicitly diagonalize the adjacency matrix, would that help you?
I think that those are not very, so you're really just saying, is it sort of a nice invertible matrix, right? The adjacency, but not complete.
I'm saying your complete graph,
yes,
is a circulant graph. It's
Yes.
like doublets and wrapped around.
Yes.
Your the ring graph is a circulant.
Yeah, the ring graph is a circulant. The complete graph is just all ones. I mean,
Right,
all,
right,
yeah.
but that's circulant also. And what came to mind is if I took a graph, if I took the ring
Yes.
graph and I connected across, and then in between, and then a quarter way. So if I took 2 to the n points, and I basically can create a graph where I have the number of edges growing like the log, the nearest neighbor is growing like the log of the,
Yes.
I could explicitly solve that, diagonalize it, and it wouldn't have the statistics you have, but it would be very interesting because
Yeah,
it's
so-
very uniform and all that.
Yeah, so this is a great question because what you're saying, what you're asking is there's this dense graph, then ours are sort of uniformly sparse, and in between is this sort of what sometimes people still refer to as sparse graphs, where the number of edges is not growing proportional to the number of, vertices, but like it's less than n, it's growing less, but it's still growing to infinity. Right, so of course these are all asymptotic limit theorems, and what we're actually interested in is in a fixed graph, right? And then we don't have any len or log n, it's just numbers, and we have to see which approximations are good, right, for that. And so it is a very interesting question, is if it's still growing. It turns out that as long as the degrees are growing, it still asymptotically converges to the mean field limit. It doesn't matter whether it's log n, log n, log. But you would have to take astronomically large n, depending on how slowly these degrees are growing, for that approximation to be good.
Right.
So it's very useful to actually think of more principled approximations beyond the mean field that would work better for lower n for graphs which are actually sparse, and that's another open question.
But here, the number of nodes is growing exponentially, but you can explicitly diagonalize. It's just an FFT to diagonalize the adjacency matrix.
Yeah,
for
but
any
it's,
choice of.
right, but it's not just that it's not the number of nodes growing is not a problem, right? Because we're anyway taking asymptotics. But I think you're saying the edges. If the edges are of order log n instead of fixed, then there is this actually even the long time behavior. There are interesting questions that even on finite time it converges to the mean field. Like if you're looking at something like the outbreak size, it actually doesn't capture it at all. Because that depends on your T and N are related, and this is not working out. So there's a whole very interesting question that there's this whole region of somewhat sparse but not fully sparse and not fully dense graphs for which we have no principled approximation. So like before we had only for dense, now we have for sort of these two regimes and sort of hybrid models. But the actual thing is if it's actually something in between where it has quite a bit of degrees, but it's not clear. And also, that's just in terms of a mathematical theorem, but then it's also about fitting a fixed n. You can think of it as log n, or you can think of it as just a fixed k. When you actually have a fixed graph with a fixed number of edges, which of these asymptotic sequences should you embed it into is a different question. For that, you need really bounds from the limit in terms of your degree sequence and things like that. So there are many, many interesting questions. This is just the tip of the iceberg.
All right, any other questions? Great, let's thank our speaker once again.
Thank you. Thank you.